Section 1 Introduction. In recent years, the impressive advances of large-scale deep neural networks have brought about a revolution in the field of artificial intelligence. These highly complex models, with millions or even billions of parameters, have exhibited outstanding capabilities in areas such as computer vision, natural language understanding, and speech recognition. These giant models are generally pre-trained on broad and substantial datasets, like ImageNet, and then adjusted for specific downstream tasks through fine-tuning or transfer learning. However, considering the immense computational resources these large pre-trained architectures need, several methods for efficient fine-tuning of parameters have been introduced. For example, low-rank adaptation, LoRA, works to reduce the number of trainable parameters by focusing only on learning pairs of rank decomposition matrices, leaving the original model parameters untouched. Adapter, on the other hand, adds a small number of task-specific parameters into a fixed pre-trained model through bottleneck adapter modules. Visual prompt tuning, VPT, introduces a minimal set of learnable parameters at the input of the transformer, keeping the backbone frozen during the fine-tuning process. However, different downstream datasets often come with unique attributes. This can include natural, specialized, or structured data, which greatly vary in their distribution and composition. A one-size-fits-all fine-tuning strategy may not account for these differences, limiting its ability to adapt to diverse datasets. To address this issue, we propose a flexible and efficient fine-tuning scheme that can handle the variability of multiple downstream datasets within one unified formulation. Our method expands on the concept of LoRA from a unified parameter-efficient fine-tuning perspective. It enhances LoRA's capability, scalability, and adaptability by scaling and shifting intermediate activations, along with applying a structural re-parameterization design. It's indeed a challenge to create a method that can handle all adjustable dimensions when tuning a pre-trained network, particularly in the case of transformer architectures. Our approach offers a practical solution to this complex issue. Our method brings several advantages to the table. 1. It simultaneously considers multiple dimensions to enhance capability and flexibility during fine-tuning, encompassing weights, features, and input tokens. 2. It significantly improves upon previous methods like NOAA and PFT by eliminating the need to retrain the subnet after an evolutionary search for the ideal configuration. This means our results are directly derived from the SuperNet's model weights, without any need for extra training. 3. It carries out an implicit search without any manual hyperparameter tuning, thus justifying the increased training time. 4. It incurs no additional inference cost thanks to our structural re-parameterization architecture, where the extra fine-tuning parameters are fused with the nearby projection weights after training. We've carried out extensive experiments on various datasets including VTA-B1K, ImageNet, and its variants. The VTA-B1K dataset comprises 19 diverse vision datasets, covering a wide range of visual domains that include natural objects, scenes, textures, shapes, satellite imagery, among others. Our method, which we call Generalized LoRA, GLoRA, surpasses all previous parameter-efficient fine-tuning methods by a significant margin in terms of average accuracy. In addition, we've tested the model's capacity for few-shot learning on 5 fine-grained visual recognition datasets and assessed its ability for domain generalization and robustness on various ImageNet datasets. GLoRA has outperformed previous methods across all these benchmarks, without incurring any extra computational overhead during the inference phase. In summary, our contributions are as follows. 1. We propose GLoRA, an innovative parameter-efficient fine-tuning framework that enhances the low-rank adaptation approach with a more generalized prompt module design per layer, offering enhanced capability and flexibility in fine-tuning. 2. We present a unified perspective of the parameter-efficient fine-tuning problem by studying various previous approaches to this task. Our proposed GLoRA framework is built based on this formulation and can handle all fine-tuning paradigms from a single formulation, serving as a one-for-all fine-tuning architecture. 3. To evaluate the effectiveness of GLoRA, we conducted extensive experiments on downstream fine-tuning, few-shot learning, and domain generalization and robustness using diverse datasets. Our experimental results show that GLoRA outperforms all previous methods on these benchmarks, while requiring only a small number of extra parameters and no additional inference cost. Section Summary. The section discusses the challenges of fine-tuning large pre-trained models on diverse downstream datasets and proposes a flexible, parameter-efficient fine-tuning scheme called Generalized LoRA, GLoRA, that enhances the low-rank adaptation approach with a more generalized prompt module design per layer. GLoRA outperforms previous methods on various benchmarks, including downstream fine-tuning, few-shot learning, and domain generalization and robustness, while requiring only a small number of extra parameters and no additional inference cost. Section 2 GLoRA. In this section, we're going to dive into a comprehensive examination of existing high-performing post-embedding fine-tuning (PEFT) methods, discussing both their strengths and weaknesses. We'll then go on to introduce a unified way of integrating all current state-of-the-art PEFT approaches, leading to our proposal of the generalized layer-wise retuning with re-parameterization and adaptation, LoRA. In essence, this method involves a design that re-parameterizes the structure for more efficient inference, with no added costs. This also involves an evolutionary search for the best layer-wise configurations, all geared towards achieving our generalized LoRA. We'll also delve into the theoretical analysis and discussions to shed more light on the higher capabilities of our proposed method. In the past, there have been some solutions that showed promise but came with certain limitations. Let's start with visual prompt tuning, VPT. This method added a small amount of task-specific parameters that can be learned to the input space, all while keeping the entire pre-trained transformer backbone static during downstream fine-tuning. There were two strategies employed by VPT, VPT shallow and VPT deep. In VPT shallow, only the input space contained the trainable prompt. This strategy kept the prompt and all other parameters frozen except for the CLS token and the image patches. VPT deep, on the other hand, allowed every layer to have a trainable prompt. While VPT deep showed superior performance on most visual tasks and had better accuracy in low data situations, it also increased costs during the inference stage. Next, we look at AdaptFormer, which introduces a parallel learnable branch comprising two linear layers and a ReLU function over the MLP block. This parallel branch is the only part that is learned, with all other parts kept static. LoRA is another method that freezes pre-trained model weights and injects trainable low-rank decomposition matrices into each layer, learning only the residual from pre-trained weight. This method achieved state-of-the-art performance when compared to prompt learning and adapters, especially with the GPT-2 model family. Scaling and shifting features, SSF, modifies features after every MLP, MHSA, and layer norm module during training. It performs re-parameterization during inference, as it follows a linear structure. While this method does not increase inference time, it has limited capability in feature adaptation. FACT uses a tensorization decomposition method to store additional weight. During fine-tuning, only the factors will be updated and stored. RepAdapter introduces lightweight networks into pre-trained models, and the additional parameters will be re-parameterized to the nearby projection weights after training. This method has a linear structure, so it can be re-parameterized, but it comes with two layers, a downsampling dense fully connected, FC, layer to downsample inputs and a group of upsampling layers for the downsample features. However, these methods have their limitations. Many of the existing PETL methods, such as VPT and adapter, increase the inference time since the proposed structure cannot be re-parameterized. Direct prompt tuning is also difficult to design as it increases computational load and requires hyperparameter tuning. LoRA can be re-parameterized at inference but doesn't scale well for larger matrices. The adaptability is also restricted to the weight space. SSF and RepAdapter can't learn the weight change, whereas LoRA and FACT can't efficiently learn the scaling and shifting of feature change. Both feature and weight space need flexibility when performing transfer learning from a large model. Our proposed method in this work aims to address these issues by tuning weight changes and feature changes, along with scaling and shifting learning for weights and features. Section Summary. The section discusses the limitations of existing state-of-the-art PETL methods, such as increased inference time and constrained adaptation ability. The proposed generalized LoRA method introduces a unified formulation that integrates all existing methods and achieves SOTA performance by injecting trainable low-rank decomposition matrices into each layer. A structural re-parameterization design is presented to show the inference efficiency without additional cost, and an evolutionary search for optimal layer-wise configurations is introduced to achieve the goal of generalized LoRA. Section 2.2 A unified formulation of one for all. In Section 2.2, titled, A Unified Formulation of One for All, we present a new, unified approach to fine-tuning models. This approach considers all possible elements that can be tweaked or adjusted in a model, such as the weight space and feature space, and not just these two. To make this possible, we utilize a strategy called re-parameterization. Here, we incorporate auxiliary parameters, or helper parameters, into the adjacent projection weights during the stage of the model's operation known as inference. At its core, our proposed method can be considered as a more inclusive version of previous solutions, hence the term, one for all. By strategically setting various support tensors to 0, our method, which we've called GLoRA, can be simplified to replicate any previous methods. Unlike another method called NOA, our method can be summarized in one comprehensive mathematical equation, which essentially represents all adjustable spaces in the model. Now, let's try to explain this equation in non-technical terms. Imagine the function of a model as a kind of machine, which we'll call f, that takes in an input, x. This machine processes the input in several stages, represented by different components in the equation. The first component is W0 plus W0, A, plus B, where W0 is a fixed quantity that doesn't change during fine-tuning, and A and B are what we call support tensors. These are adaptable elements that we can train to improve the model's performance on specific tasks. In particular, A is used to adjust the weight of the model, while B modifies the input and shifts the weight. The second component is C, W0, where C is another support tensor serving as a layer-wise prompt, akin to the function of VPT deep. The third component is D, B0, plus E, plus B0, where D and E are yet another pair of support tensors that are used to scale and shift the bias, and B0 is another fixed quantity. By understanding how these components interact, we can better fine-tune the model. A more detailed depiction of this process is given in the figure. Please note that this is a simplified explanation of the complex mathematical equation provided in the paper. The actual implementation and understanding of this method require a good understanding of machine learning concepts and mathematical knowledge. Section summary. The authors propose a unified formulation for model fine-tuning that includes all tunable dimensions, such as weight and feature space, and incorporates auxiliary parameters during inference. Their method serves as a superset of all prior solutions and can be reduced to any of these predecessor methods by setting different support tensors to 0. The consolidated formulation is represented by a unified mathematical equation that includes trainable support tensors for downstream tasks. Section 2.3 Prompt Modules. In this section, we'll outline our approach to creating layer-by-layer adjustments, or prompt modules, for 5 elements, A, B, C, D, and E. These prompt modules can be thought of in a variety of ways, including as simple numbers, scalars, arrays of numbers, vectors, decompositions of matrices into simpler forms, low-rank decompositions, or even as absent, none. Depending on the function of these adaptable tensors within the model, we can categorize them as follows. A could be a low-rank decomposition, LoRA, a vector, a scalar, or none. B could be a low-rank decomposition, a vector, a scalar, or none. C could be a low-rank decomposition, a vector, or none. D could be a vector, a scalar, or none. E could be a vector, a scalar, or none. None here implies that if all adaptable tensors are 0, the model simplifies back to its original form. Let's dive a bit deeper into the mathematics. We have a square matrix W with dimensions dxd. We define new matrices A, B, C, C, which are all dxr dimensional, as well as vectors D and E, both of which are dx1 dimensional. If we're using a low-rank adjustment, LoRA, and the rank is less than R, let's call it R, we create new matrices A and A with dimensions dxr and rxd, respectively. These matrices are extracted from A and A. The final tensor A is then the product of these two matrices. In the case of a vector, we use a dx one-dimensional slice from A to form A, and if it's a scalar, we extract a single value from A to form A. This same process is applied to the other tensors, B, C, D, and E, depending on the configuration we're using for our model at any given moment. This method of weight entanglement, where parameters are shared across different subnetworks, allows us to broaden our search space without a significant increase in the number of parameters. It also leads to quicker convergence of the model during training. Section summary. The methodology for designing layer-wise adapters or prompt modules for A, B, C, D, E can take the form of scalars, vectors, low-rank decompositions, or none. Depending on the current subnet configuration, weight entanglement strategy is followed to increase the search space without increasing the number of parameters substantially, and also shows faster convergence due to weight sharing in different subnets. Section 2.4 Structural Re-parameterization Design and Inference Efficiency Analysis. We're going to delve into Section 2.4, which talks about the design of structural re-parameterization and its effects on the efficiency of inference. The crucial element that allows re-parameterization to happen is the removal of non-linearity between consecutive transformations. This removal allows additional parameters to be integrated into the previous ones. As highlighted in the rep adapter study, getting rid of these nonlinear layers doesn't negatively affect the network's performance. In simpler terms, we can describe the re-parameterization in GLoRA as follows. Imagine a function f that takes in x and gives us a result. This function depends on two elements, a trained weight and a bias, which we'll call w_uni and b_uni. The function f is then defined as the product of w_uni and x plus b_uni. Now, w_uni and b_uni are re-parameterized, that is, they're expressed in a new way. We define w_uni as the sum of an original weight, w_0 feet, the product of w_0 feet and a parameter a, and another parameter b. Similarly, we define b_uni as the sum of the product of a parameter c and w_0 feet, the product of d, and an original bias, b_0 feet, a parameter e, and b_0 feet. Our re-parameterization approach, which blends learnable parameters with nearby projection weights, proves to be beneficial. It doesn't require extra computational resources during the inference stage, thereby increasing efficiency. Moving on to section 2.5, which is about the evolutionary search for optimal layer-wise configurations. Our unified adapters design is implemented on each layer individually, which allows variability across different layers. To find the best configuration for each layer, we use an evolutionary search technique. This method provides a mix of efficiency and effectiveness. While this approach may extend training time, it's important to understand that other studies also require a comprehensive search for the best parameters. Examples include the low rank in LoRA and FACT, as well as the position and size of adapter modules in adapter, and the structure configuration in RepAdapter. In our case, we use a weight-sharing method where a single large matrix is set for each support tensor. Depending on the component, LoRA, vector, scalar, or none, a smaller matrix is selected and used for the current training cycle. This approach boosts parameter efficiency as it allows maximum weight sharing in the subnets. In contrast, our unified prompt module design carries out an indirect search, eliminating the need for manual adjustment of parameters. Thus, any increase in training time is justifiable and well worth it. Section summary. The re-parameterization design used in GLoRA eliminates non-linearity between adjacent transformations, allowing for the absorption of additional parameters into preceding ones without impacting network performance. This strategy incurs no additional computational cost during inference. The evolutionary search method is employed to identify the optimal configuration for each layer, allowing for heterogeneity across different layers and eliminating the need for manual hyperparameter tuning. Section 2.6 GLoRA with higher capacity. In section 2.6, we discuss how to give our model, GLoRA, more capacity. Capacity, in this context, means the model's ability to approximate a broad range of functions. One way to control the capacity of a learning algorithm is by carefully selecting an appropriate hypothesis. Space. Think of this as the set of all possible solutions that the learning algorithm is allowed to explore. A tool we can use to formally support this approach is the Vapnik-Chervonenkis dimension, or VC dimension. This measures the capacity and complexity of a statistical algorithm. Let's think about a theorem related to this. Suppose we denote the VC dimension of our hypothesis by dVC, h. If our current hypothesis space Hi is a part of a larger universal hypothesis space, Honey, then the difference in VC dimensions between the two should be greater than or equal to a value epsilon, where epsilon is a non-negative number. This theorem holds true because of the specific nature of our problem. Here, our current hypothesis space Hi is indeed a subset of the universal hypothesis space, Honey. This universal hypothesis space includes all possible scenarios that could be covered by Hi. Now, consider an extreme case where the VC dimension of the difference between Honey and Hi, denoted by dVC, Ho, equals 0. In this case, the error epsilon is also 0. According to learning theory, a higher VC dimension means our model has greater flexibility and ability. Therefore, increasing the VC dimension is one way to enhance our approach. Section summary. The capacity of a model refers to its ability to approximate a wide range of functions. To regulate the capacity of a learning algorithm, an appropriate hypothesis space must be selected. The Vapnik-Chervonenkis dimension, VC dimension, can be used to measure the capacity and complexity of a statistical algorithm, with a higher VC dimension indicating greater model flexibility and capability. Section 3 Experiments. In our third series of experiments, we thoroughly test GLoRA, our model, using the VTAB1K benchmark at various levels of parameter counts. VTAB1K is composed of 19 different tasks related to image classification. These tasks fall into three distinct categories: First, natural images. Second, specialized tasks that include remote sensing and medical datasets. Third, structured tasks that emphasize understanding the structure of a scene, such as predicting depth or orientation. We also assess GLoRA's performance on 5 datasets specifically designed for fine-tuning visual recognition in a few-shot scenario. These datasets include Food 101, Oxford Flowers 102, Stanford Cars, Oxford Pets, and FGVC Aircraft. As done in previous studies, we evaluate our model using 1, 2, 4, 8, and 16-shot settings. To demonstrate the ability of GLoRA to generalize across domains, we train the model on ImageNet using a 16-shot setting and then test it on ImageNet v2, ImageNet Sketch, ImageNet A, and ImageNet R. As for the architecture and implementation details, we use the VIT-B model pre-trained on ImageNet 21K for all of our experiments. VIT-B is a transformer model comprised of 12 blocks, each containing multi-head self-attention, MHSA, and multi-layer perceptron, MLP, modules. Both MHSA and MLP modules include 2 linear layers, which means each block has 4 linear layers in total. We implement GLoRA across all 4 layers of the 12 blocks, making a total of 48 GLoRA-adapted linear layers in our final model. It's important to stress that GLoRA can be added to any linear layer in any network architecture. Our method requires minimal tuning of hyperparameters, with the exception of those related to the optimizer. Relying on previous works, we utilize the Atom W optimizer in all our experiments. We set weight decay at 0.0001 and adjust the learning rate to either 0.0001 for larger datasets or 0.0005 for smaller datasets. Learning rates for specific datasets can be found in our supplementary material. We train our models for 500 epochs with a fixed batch size of 64 using a cosine learning rate scheduler. It's crucial to note that this strategy proves effective across all dataset settings. Additionally, we don't retrain the weights after the search process and directly use the weights from the trained models for evaluation. This means all models for different datasets are only trained for 500 epochs in total. The appendix contains a comparison of the time cost for search and training with other methods that also use search-based approaches. Section Summary. The GLoRA model was evaluated on the VTAB1K benchmark, consisting of 19 image classification tasks clustered into 3 domains. The model was also tested on 5 fine-grained visual recognition few-shot datasets and showed domain generalization capabilities when trained on ImageNet and tested on ImageNet v2, ImageNet Sketch, ImageNet A, and ImageNet R. The GLoRA model was implemented on all 4 layers across the 12 blocks of the VIT-B pre-trained on ImageNet 21K, accounting for 48 GLoRA-adapted linear layers in the final model. The model was trained for 500 epochs with a fixed batch size of 64 and a cosine learning rate scheduler, and the weights were not retrained after the search process. Section 3.1 VTAB1K Dataset. In this section, we'll focus on the VTAB1K dataset, using it to train 3 distinct configurations of our model, GLoRA, or the Global to Local Representation Adaptation model. These different configurations essentially modify the number of parameters we're able to fine-tune, thereby providing users with the ability to customize the final model to their specific needs. The distinction between these configurations lies in the dimensions of the local to global representation adaptation, LoRA, present in the model search space. In the most extensive model, the LoRA dimensions are 8 and 4, in the mid-sized model they're 4 and 2, and in the smallest model, it's only 2. Let's now turn our attention to the results. When we ran these configurations on the VTAB1K benchmark, we found some interesting outcomes, as you can see in the included table. Remarkably, our approach pushes the boundary of what's currently achievable in transfer learning that is both efficient and parameter-oriented, outdoing existing methods by up to 2.9%. Indeed, even the smallest configuration of our model outperformed all existing methods by a noticeable margin. It's worth mentioning that GLoRA has shown impressive performance across different datasets. This is in stark contrast to other existing methods which tend to falter on at least one dataset, confirming GLoRA's impressive ability to generalize. We've found that GLoRA leads the field in as many as 14 out of the 19 datasets in the VTAB1K benchmark. Furthermore, it delivers competitive performance on the remaining datasets. Section Summary. The authors trained 3 GLoRA SuperNet configurations with varying numbers of trainable parameters, achieved state-of-the-art results on the VTAB1K benchmark, and outperformed existing methods even with their smallest model. GLoRA also demonstrated high generalization capabilities, performing competitively across datasets and pushing the state-of-the-art in as many as 14 out of 19 datasets in the VTAB1K benchmark. Section 3.2 Few-shot learning. In section 3.2, we delve into the performance of GLoRA when we have limited data available, which we refer to as few-shot learning. We pit GLoRA against other methods, such as LoRA, adapter, VPT, and NOAA, focusing on its effectiveness on fine-grained visual recognition datasets. The number of data points, or shots, used in these comparisons range from 1 to 16, with the results visualized in the accompanying figure. GLoRA stands out by consistently outperforming other methods across the majority of the few-shot learning datasets, even when the methods used have similar parameter counts. The exception is on the Flowers 102 and Food 101 datasets, where GLoRA's accuracy matches that of the other methods and NOAA respectively. This is due to the fact that the overall performance on these datasets is already exceptionally high. Even when the number of shots is low, the performance improvement with GLoRA is still significant. And as we increase the number of shots, this performance boost becomes even more noticeable. In the following section, 3.3, we turn our attention to the concept of domain generalization. This is a measure of how well our model can apply what it has learned to unfamiliar datasets, which is a crucial attribute for large-scale neural networks intended for real-world applications. Models that have been fine-tuned using PETL methods should exhibit this enhanced ability. We demonstrate the domain generalization prowess of GLoRA by testing it on unfamiliar datasets using a model that has been fine-tuned on the ImageNet-1K dataset. As in previous research, we restrict the number of training examples per class to 16 for this experiment. Despite these limitations, GLoRA manages to come close to the performance of the fully scaled ImageNet-1K fine-tuned model, which stands at 83.97%. Even in a 16-shot setting, GLoRA reaches a performance level of 78.3%, showing that it excels at few-shot learning even on large-scale datasets like ImageNet. Furthermore, the performance on unfamiliar datasets sees a substantial increase compared to existing methods. For instance, when comparing GLoRA to LoRA, GLoRA doubles the performance on the ImageNet dataset and increases it by 50% on the ImageNet Sketch dataset. This shows that GLoRA not only excels at domain generalization but also performs exceptionally well in few-shot learning scenarios. Section summary. The performance of GLoRA on fine-grained visual recognition datasets as few-shot learning is presented, and it outperforms existing methods by a large margin with similar parameter counts. GLoRA also demonstrates superior out-of-domain generalization capabilities, narrowing the performance gap even within a 16-shot setting and enhancing out-of-domain performance by as much as 100% ImageNet A and 50% ImageNet Sketch when compared with LoRA. Section 3.4 Analysis and Discussion. In this section, we'll discuss the computational cost and performance of various prompted evolutionary fine-tuning (PEFT) methods, including GLoRA, our method. These tests were performed on a high-end graphics processing unit, specifically the NVIDIA 3090 GPU. What's noteworthy here is that GLoRA outperforms the rest. It does so because it does not require additional computational resources, parameters or floating point operations during the inference process. This makes GLoRA quite versatile, especially in real-world settings where models are already in use. What's more, GLoRA can simply be added to existing models, without the need for any manual modifications to the system. We've also developed GLoRA to be compatible with deeper prompts, through the use of a support tensor, denoted as C. But this does not increase computational costs, thanks to GLoRA's efficient re-parameterization design. We'll now take a look at how parameters are distributed in the different linear layers of the vision transformer model, referred to as VIT-B. Here, the projection layer has the least number of adjustable parameters across 1,000 different categories, denoted as VTAB1K. Overall, the multi-layer perceptron (MLP) module contains more parameters than the multi-head self-attention (MHSA) module. However, we found that our structured group requires more parameters to adapt to changes due to significant variations from the ImageNet-1K dataset. The GLoRA algorithm uses support tensors to determine how each layer of the model should be adjusted. Every layer can have up to 72 distinct adaptations across datasets. Interestingly, support tensors D and E do not change much because they often don't need to adapt, while A and B adapt more frequently. But there is no clear pattern as to which type of adaptation is most common. Importantly, even a simple number can be used effectively as a support tensor, allowing GLoRA to adapt each linear layer while still being efficient in its use of parameters. Despite the impressive capabilities of GLoRA, there are a few limitations worth mentioning. For instance, the use of evolutionary search in GLoRA makes the training process longer. However, this is counterbalanced by GLoRA's negligible need for hyperparameter tuning and manual architectural design. GLoRA's architecture is flexible, allowing it to be used for a variety of tasks in computer vision and natural language processing. We have not explored these applications in this paper, however. Also, we have not discussed how GLoRA can be adapted to convolutional layers in this paper, but this should be relatively easy to implement, following the principles outlined in our equation. Section summary. The final inference cost of various PEFT methods is shown in a table, with GLoRA outperforming other methods due to its zero parameter or flops overhead during inference. GLoRA also supports VPT deep-level prompts via the support tensor, C, and can be easily adapted in real-world scenarios without manual system modifications. However, a primary limitation of GLoRA is the evolutionary search procedure, which increases the total training duration, and its adaptability to convolutional layers is not detailed in this paper. Section 4. Related work. The rapid increase in model size in the realm of natural language processing, NLP, has led to the emergence of many techniques for efficient fine-tuning of these sizable language models. These methods for parameter-efficient fine-tuning, PEFT, have proven their effectiveness in a wide array of tasks within NLP. Similarly, with the expansion in the scale of image models, approaches designed especially for these models have also been introduced. Among them, LoRA, or localized randomized attention, stands out for its ability to be applied successfully across different models and tasks. One of the reasons for this is LoRA's simple design strategy, which operates directly on weight tensors and is independent of the model type or its settings. Furthermore, LoRA does not add any extra inference parameters or latency caused by what's called structural re-parameterization, unlike some other techniques such as adapters or prompt tuning. Techniques like RepAdapter and SSF also propose a structural re-parameterization design for efficient fine-tuning. However, the RepAdapter technique is model-specific and requires manual design for different layer configurations. On the other hand, SSF serves as a simple starting point, but it faces limitations in its adaptability and capability due to its adaptation being restricted to the activation space. FACT is another technique that refines LoRA's matrices for improved parameter efficiency. However, we assert that a parameter scale less than 1 million is already quite efficient for fine-tuning on a single GPU. Thus, considering LoRA's benefits over other similar techniques, it's crucial that we focus on enhancing LoRA's flexibility, scalability, and adaptability. Section summary. The field of NLP has proposed many methods for parameter-efficient fine-tuning, PEFT, of large language models, LLMs, due to the exponential growth in model size. LoRA is a method specifically focused on image models that has proven to transfer well across modalities and tasks, partly due to its simplistic design strategy that directly works over weight tensors, irrespective of model type or configuration. Compared to other related works, LoRA doesn't add any additional inference parameters or latency due to structural re-parameterization (SR) design, making it more advantageous.